In this lesson, we're going to explore similar right triangles and how those can be used to solve problems. So the last unit we did was all about similar triangles, and this unit's going to be about right triangles. So this is our introduction to what we're going to be doing in this unit. So the first thing we're going to talk about is how these right triangles are similar, what's being done to make them similar. So our first theorem here is theorem 9.1, which says if the altitude is drawn to the hypotenuse, so the altitude is this ray right here, CD. So with the endpoints C and D, that would create the altitude. So this segment right here is the altitude. So just a reminder, the altitude is a segment drawn from the vertex that is perpendicular to the hypotenuse. So notice that down here it's meeting at a right angle. So if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles that are created are similar to the original triangle and to each other. So in this figure, by drawing that altitude, we've really created three triangles. We have triangle ADC, which is the smallest triangle of the three. So that's the smallest triangle of the three because it is connected to the smaller leg. So we have triangle ADC, and then we have triangle CDB. And so that is going to be the inside triangle that's connected to the longer of the two legs. And then the final triangle we're looking at is the overall triangle. So the big triangle that these two triangles are within. So that final triangle is triangle ACB. And so all of those are written with the right angle in the middle as the kind of vertex, if that was an angle. And so those three triangles are similar triangles, the two smaller ones created by the altitude and the original large triangle. So 9.1 gives us that similarity statement where all three triangles are similar. So now we're going to use this to create more theorems. So theorem 9.2 says the length of the altitude, so the length of the altitude, let's call that x, is the geometric mean of the lengths of the two segments of the hypotenuse. So if we call these two segments, like, let's call these A and B. So it's the geometric mean of those two segments. So what that means is that if we're doing the geometric mean, we multiply things together and then take the square root of them. So how that looks as a ratio is that since that length of the altitude is the geometric mean, I'm going to put those x's in the mean spots, and then I'm going to put those two pieces of the hypotenuse in the extreme spots, which is the bottom of the first and the top of the second. So I'll put A at the bottom of the first ratio and B at the bottom of the second. So when you do cross products, that says x squared equals the product of A times B, and then x would equal the geometric mean, which is the square root of the product. So that's theorem 9.2 that says that. The next theorem we have is theorem 9.3. So this one says the length of each leg of a right triangle, so the length of each leg of the right triangle, let's call AC our first leg that we're going to be working with. So the length of each leg is the geometric mean. So I'm going to put that variable for the leg on the top of the first one and the bottom of the second one. Those are in the mean positions of that proportion. It is the geometric mean of the length of the hypotenuse and the segment of the hypotenuse adjacent to the leg. So it's the geometric mean of the length of the hypotenuse, which would be this whole segment. Oops. So I could say that that is A plus B. And the segment that is adjacent. So if I'm looking at segment Y, the leg that is labeled Y, the segment that's adjacent is A. So if I named this other leg Z, I can also set up a ratio for the geometric mean there. And so it would be the length of the hypotenuse, which is both pieces together, and the piece that is adjacent. So adjacent to this segment that I've labeled Z is segment B. So this would end up as y squared equals a times a plus b, or y is the square root of that product. And for z, that would be z squared equals b times a plus b, or z is the square root of that product. So these geometric means are coming back, and that's how we're going to use them. Oops, so this is theorem 9.3 for these pieces, and that one is theorem 9.2. So we just need to identify like what we're looking at, what we need to write down whenever we start a problem. All right, so example 1 here says write a similarity statement for the 3 similar triangles in the diagram and then complete the proportion. So let's start out with our big triangle. So we're just going to choose one triangle to name, and to kind of keep it the same, I'm going to look at this triangle and I'm going to choose a starting point. So if I choose to start at A, so triangle A, and then I need all 3 letters. So maybe I'm going to go down this leg to the right angle. So down that leg and to the right angle is going to be to C. And it looks like AC is a little bit longer than BC. So I'm going to say that this is the longer leg. And then I'm going to go from C out to B, which is the shorter leg. So ACB goes down the longer leg to the right angle and then down the shorter leg. So I need to write the similarity statement, which is going to compare it to these other triangles as well. So maybe I'm going to look at this one that's on the top portion here. So it's segments or points A, D, and C. I just need to figure out which order to put them in. So in this triangle, it looks like the longer leg of this triangle is going to be AD. So these are pretty close. It's a little bit harder to figure out what the closest part is. But if that is the longer leg and I want to go to the right angle, I'm going to say AD and then up to C. And then I'll work with my last triangle, which is this one here. And so for this last triangle, it looks like maybe this side is the longer piece. So I'm going to go C, D, B to name this last triangle. So I know that the right angle needs to be the middle letter. So C to D is looks a little bit longer than D to B. That's how I chose to name it. So based on this, if I set up my first ratio as AD to CD, both of those are segments within the green triangle. So AD to CD is the longer to the shorter leg of the green triangle. So AD to CD. Then the next thing has DB in its lettering. So, and so as we name segments, we can name those in any order, but we do want to look at which triangle we're working with. So this one is the orange triangle that has DB in it. And so DB is the second piece, so the first piece would be CD. So AD over DB equals CD over DB. So you just figure out what those proportional parts are. All right, example 2 says the roof of a house has a cross section that is a right triangle. So this is like if you were looking at the roof of the house and you just took like one slice, one set of those beams. So what we have here is we have the roof of the house, like here's the slope on the front, here's the slope on the back, and then this would be like the height the top of the walls. And so if we need to put a support beam in, we would want to make sure that that's perpendicular. So what that's going to do is it's going to create this similar right triangle situation. So the roof of a house has a cross section that's a right triangle. Let's identify those right triangles that are similar. So here in the big triangle, B is my right angle. And then I can see that A to B is shorter than B to C. So that can kind of be my guide. Triangle ABC can be the first one I name. And then I just want to name the rest in that order. So I'm going shorter side to the right angle and then down the longer leg. So if I look in the next triangle, let's use A, B, and D as our next three letters. So I look where the right angle is. And A to D is shorter than B to D. So I'm going to go down the shorter side, A, D, and then up the longer leg to B. A, D, B would be that second triangle. And then in our third triangle, the triangle that's on the right inside, the right angle is at D. So the shorter leg looks like it starts at B. And then I'm going to go to the right angle, D, so down the shorter leg, and then across that longer leg, which is to C, DC. All right, next we're going to find the value of H. So H is segment BD. So segment BD, I can use either of these triangles that have BD as part of them. But let's go on and say that we're going to start with BD. And then I want to use our proportional parts. So other segments that I know that AB is 7.8, so AB. And I know that BC is 12.3. So anything that has BC in it, I can also use that. And I know that AC is 14.6. So looking at what I have several options here that I can use. So maybe I want to use, I'm just choosing two triangles. Maybe I want to use triangle ABC because I know all three lengths of that triangle. And then maybe I want to use this second triangle. So the triangle that has DB or BD in its ratio is this second triangle here. And so I'm going to put that over AB because I know that length is 7.8. So I did DB and then I did AB. So similar to DB in this first triangle is BC. Those are the last two letters. And then in the same spots as AB in this first triangle is AC. So I just choose a ratio to start with where I'm going to know things that I can plug in, and then I'll solve with what I have. So the length of BD, is represented by this variable H. I'm going to plug that in. Then the length of AB is 7.8 meters. The length of BC is 12.3. And the length of AC is 14.6. So since I set these ratios up in this way, now I can solve. So I'm going to multiply my cross products, 14.6H. It's going to be equal to, since I'm working with decimals, I'm going to pull up my calculator. And so that's 7.8 times 12.3. So that's going to give me 95.94. All right, so to figure out the value of H, I'm going to divide by 14.6 on both sides. So 95.94 divided by 14.6. That's not a super nice decimal, but I'm going to take my lead from these. All of these are measured to the tenths place. So I'm going to round this one to the tenths place. So H will be, I'm going to say approximately, since I'm rounding, approximately 6.6 meters. So I also could use this fraction, which isn't very nice, But since all of these numbers were rounded to the nearest tenth, I'm going to round my number to the nearest tenth as well. So that support beam that's put in from B to D to help hold the roof up would need to be 6.6 meters long. All right, so now we're going to start applying that Theorem 9.2 and Theorem 9.3. So Theorem 9.2 was about the altitudes, and Theorem 9.3 was about the legs. So I just need to identify which theorem I'm using and then put it into action. All right, so this one, I noticed that the segment that connects the right angle down to the hypotenuse, and that means that it's perpendicular, this is an altitude. So this is going to use Theorem 9.2. So Theorem 9.2 says that the length of the altitude, so it's going to be altitude. The altitude is the geometric mean of the two pieces of the hypotenuse. So it's going to be piece 1 and piece 2 in the other two spots. So the two pieces of the altitude are of the hypotenuse. All right, so now let's plug in things that we know. So the length of the altitude is represented by the variable x. And then piece 1, I can choose either one as piece 1. I'm going to choose 6 as this piece and 10 as the other piece. So now that I have this set up as a ratio, I can use my cross products to solve and figure out the value of x. So when I do that, I'm going to have x squared equals 6 times 10, and 6 times 10 is 60. Then to get that x by itself, that's going to take the square root. So let me change colors so we can see that this is a different step. So I'm going to take the square root of both sides. So I kind of have two options here. I can reduce this radical here by its greatest common factor. That's a perfect square. Or I can estimate it. So let's think about both parts. So I know that 60 is divisible by 4, and 4 is a perfect square. So if I divide 60 divided by 4, I get 15. So then I'm going to think about 4 is a perfect square, and the square root of 4 is 2. So that perfect square goes on the outside, and then the piece that's left over goes on the inside. So 2 root 15 is the exact value of x, and then I can also estimate it. So I can do the square root of 60, which gives me 7 if I go to the hundredth, 7.75. And notice that if I type in that reduced radical version that we did, we get that same thing because it's the same number. So just depending on how your directions ask you to give the answer, it could be either of those answers. So 2 root 15 is the exact answer, and 7.75 is the estimated answer, or rounded. All right, so we just set up that ratio and then solved it. I'm going to keep my calculator up because all of these are about geometric means. All right, looking at this next problem. What I see is that y is a leg. So since that's a leg, that's going to be using 9.3. So 9.3 said that the length of a leg of a right triangle where the altitude is drawn is going to be the length of the hypotenuse times the adjacent piece. So it is the geometric mean of the hypotenuse and the adjacent piece of the hypotenuse. All right, so we're going to drop in these parts that we know. So the leg here is represented by the variable y. So both of those things that say leg, the leg that I'm working with is y. And then the length of the hypotenuse is going to be the whole thing. So this whole hypotenuse, I'm going to add those two things together. 5 plus 18 is 23. So I'm going to drop that into this first spot. And then the adjacent piece means the piece that touches this leg. So the adjacent piece here is going to be the 18. So as I get that set up, now I'm ready to find that geometric mean. So y squared is going to equal 23 times 18. Type that into the calculator. So that's 414. Let me go in and replace that. And then to solve that, I find the square root of both sides. So the square root cancels it out and gives me y by itself. Then I have the square root of 414. Now 414 is one that I don't know a whole lot about. So if I think about 414, I'm going to think about some perfect squares that I can see if we'll go into it. So the first one I think of is 81. Notice that 81 does not come out as a whole number. So that's not the correct perfect square. Next, let's try 36. Closer, but not quite. What about 16? 16 doesn't work. What about 4? 4 doesn't work. 9 works. So 9 will give us 46. And 46 isn't divisible by any more perfect squares. So the factors of 46 are 2 and 23, which are both prime numbers. So that's going to be as far as it can go. So outside, I put the square root of 9, which is 3. 3 times 3 is 9. And then inside, I put that part that's left over. So the exact answer is 3 root 46. Or I can estimate that. And I can estimate it from the original or from that reduced version we just did, and it should give me the same answer. And it does. So my estimated version, and if I round to the nearest hundredth, that'll be 20.3. And then since that third number after the decimal point is more than 5, it'll round that 4 up to a 5. So 20.35. So just depending on what your instructions say will help you figure out what you need. All right, so looking at where my length is, here I have a length for the altitude. So this is 9.2, that fills with altitudes. So that one said that the altitude is the geometric mean. So that means that the altitude goes in the top of one and the bottom of another. And it is the geometric mean of the two pieces it creates. So piece 1 and piece 2. All right, so in this one, our variable is not the altitude. So instead, we're just going to put in piece by piece. The altitude measurement is 20. So I'm going to put that at the top of one and at the bottom of another one. Then I'm going to put my two pieces in the other spot. So piece 1, I'm going to say is the 12, and piece 2 will be the x. So now with this setup, I'm not going to have a square, like a x squared in this one. I'm going to have a 12x equals 20 times 20, which is 400. All right, so I'm going to divide that by 12. And x equals, so 400 divided by 12. This is not a good decimal, so unless it tells us to round, we don't want to use the decimal. So if it does say to round, we can round to the nearest hundredth, which would be 33.33. If it doesn't say to round, we're going to use that fraction version. So this is reduced to 100 thirds, and 100 thirds would be 33 and 1/3. So that 0.3 repeating at the bottom of our, where we estimated it, that is 1/3. So 33 and 1/3. All right, on the last one here, we're given the length of a leg. So since it's dealing with a leg, this is going to be theorem 9.3, which says that the length of the leg is the geometric mean of the hypotenuse and the piece adjacent. All right, so in this one, I was given the length of the leg. The length of the leg is 32. So I'm going to put that at the top and the bottom. Then I need a expression for the entire hypotenuse. So the two pieces are 15 and x, so the entire hypotenuse would be 15 plus x. We would add those together. And then the piece that's adjacent, I look at the leg that I'm working with, and then the piece that's adjacent is 15. All right, so when I do cross products, first I'm going to do 32 times 32, which is 1,024. And then I'm going to distribute here on the other side. So that's 15 times 15 plus x. So if I distribute, 15 times 15 is 225, and then 15 times x is 15x. So I have 1024 equals 225 plus 15x. So first I'm going to subtract that 225 from both sides. This will be 1024 minus 225. That's 799 divided by 15. So 799 divided by 15. Not a nice decimal. If it tells me to round, I'll do that. And let's say it says it to the nearest hundredth again. So that would be 53.2. That 6 is going to round up to a 7. Or I can use this decimal version, which it doesn't reduce. So 799 over 15. Or I can use this decimal version to help me out. So it tells me that it can go in 53 times. And then I'm going to do 53 times that denominator of 15, which is 795. So the whole part is 795 of the 799. So that leaves 4 15ths left over. So those are acceptable answers. You only want to round it if it tells you you can. So that's how we can use those theorems to help us solve for missing pieces of right triangles.